Okay, so today we're going to talk about reactive agents. Thank you for braving the weather to come in today. So we'll look at the history of reactive agents, Breitenberg vehicles, we'll look at examples of reactive agents in nature, chemotaxis, and then we'll have a look at behavior-based robotics. So if you remember, these reactive agents are agents which don't have any memory or planning, they just simply choose their next action based only on what they currently perceive. Using a policy or a set of rules that are simple to apply, they can't remember, they can't plan, they can't logically reason, but it turns out that interesting behaviours often emerge from these simple rules. Now, Alan Turing is a ubiquitous figure in artificial intelligence, as well as all the other things that he did. He also wrote an essay very near the end of his life in which he emphasized the importance of embodiment to artificial intelligence, that perhaps you need to have a body and you need to be able to move around the world and experiment with things in order to learn and develop intelligence. Then Herb Simon in 1969 in this book, The Sciences of the Artificial, one of the things in that book, he talks about complexity that emerges between an agent and its environment. So what he talks about is actually an ant. If you sit and watch an ant crawl around on a beach, you see that the ant is taking a very complicated path. So you would think the complexity should be in the ant, but actually the ant itself is following very simple rules. The reason that the path is complicated is because at that level of granularity, the environment is very complicated. It's walking up and down over these grains of sand and so on, which are quite large compared to it. And so it's just this idea that complexity emerges from an interaction of the agent and the environment, not necessarily inherent to the agent. Now, I mentioned Rodney Brooks, Intelligence Without Reason, but in fact a similar point of view was put forward even earlier by Valino Breitenberg. His book Vehicles was published in 1984, but it was based on manuscripts from lectures that were given much earlier, I think perhaps as early as 1968 even. And in the mid-90s, some of these ideas were embodied into these Lego Mindstorm robots, and Lego actually sponsored a professorship at the MIT AI lab. Seymour Papert was the Lego professor of artificial intelligence for some years. So what was it that this Breitenberg did? Well, he was interested in the idea of how you could build up simple vehicles from these kind of electrical circuits that connect up sensors to motors. And in his book, he starts with simple vehicles and then gradually builds up to complexity, but we're just going to have a look at the first few vehicles that he describes. And the idea is that they have a sensor which responds to a light source, and the response is inversely proportional to the distance from the light. So if the sensor is not facing towards the light, the reading is 0. If it is facing towards the light and is very close to the light, then it has a very high reading. If it's very far away from the light, the level of the signal diminishes. And so here's an example of some of the vehicles that he described. So the first vehicle is like this. You have, okay, so there's two wheels here, and the left wheel and a right wheel, and then there's two light sensors at the front. And the rights, they're crossed over. So the right sensor is connected to the left wheel, the left sensor is connected to the right wheel, and they have a positive effect on the vehicle. So if the light sensor reading is high, it makes the wheel spin faster, and if it's low, it makes the wheel spin slower. Okay, so let's think about this. Let's suppose the vehicle is sitting here, the light source is there. Tell me what behavior you will observe from this vehicle.
It'll turn towards the light and go forwards.
That's right. So it'll go forwards. So because it's detecting the light, it'll go forwards, and the right sensor is detecting the light more strongly. So that means that the left wheel will spin faster, so it will actually turn towards the light. And not only that, but as it goes towards the light, it will it speed up or slow down?
Speed up.
Speed up, that's right. So he called this the hate vehicle because it'll turn around towards the light and run towards the light and go faster and faster and just smash into the light. So he called this hate. Now, this is just anthropomorphizing. It's really just these little connections here, but somehow when we watch it, we really feel as if it is showing these emotions, right? Now, what happens, this is a very similar vehicle, but instead of being crossed over, it's just direct connection. So this is connected to here, that's connected to there. So what is this vehicle going to do? Yeah.
Go away from it.
Move away from the light. Right. So this it feels the light more strongly on this sensor, so that wheel will turn faster. So that means it'll turn away from the light, and it's traveling very fast when it's close to the light, and then when it gets far away from the light, it'll stop. If it gets to a dark place where it doesn't sense any light, it won't move at all. So it likes to run away and hide in the shadows, behind a curtain or something like that. So that's why we called it fear, right? So we've got hate and fear. Now, then we can modify things a little bit more. We can have negative effects from the sensors to the motors. So what you have to imagine here is that with no light, the vehicle will move even in the absence of light. It'll move at some fixed baseline speed, but then when it detects the light, it'll actually slow down from that speed, right? So this vehicle has connections going directly from left to left and right to right, but it has this negative influence instead of positive. So what will this vehicle do?
Turn towards the light and slow down.
That's right. It'll turn towards the light. The behavior is different from the hate. The hate vehicle will speed up and smash into the light. This thing here, it just it sees the light. It turns around to face the light, and then when it gets close to the light, it just stops. It just sits there and worships the light. It adores the light, loves the light. So we call this vehicle the love vehicle. And the final combination is where it's negative and crossed over. So what does this vehicle do? Well, it turns away from the light. But again, its behavior is different from the fear vehicle because this one actually slows down as it gets towards the light. So you can sort of imagine this vehicle as like an interstellar voyager. As it's traveling through the darkness of space, it travels at its maximum possible speed, and then when it gets close to a star, it will slow down, go quite close to the star and slow down so that it can have a good look at that star, and then afterwards it'll speed up again and shoot off looking for another star. Right now, Breitenberg initially called this the wandering vehicle or wandering behavior, but because the other three vehicles are named after emotions, we prefer to have an emotion for this one as well, so we call it curiosity. So we've got hate, fear, love and curiosity. So this is a very interesting observation that just from these simple circuits you can get these behaviors that look very emotive to us. Now, by the way, this concept of having things crossed over like this, that may seem a bit strange at first, but this does actually occur in nature because, first of all, within the eye, the image on the back of the eyeball is actually inverted. Okay, so if because light coming in from the right side of your body falls on the left side of the retina and vice versa. So it happens within the eyes. But in fact, there's a kind of crossover that happens at the level of the brain as well. It turns out that the information from the right eye is predominantly processed in the left half of the brain, and the left half of the brain also controls the right side of the body predominantly. So the left side of the, if you have an injury to the left side of the brain, it will affect your right arm and your right leg and vice versa for the right side of the brain. And when you first think about this, it seems irrational. You think it would be more efficient to if the brain were wired up directly rather than having all these cross connections. So it's an interesting question, well, why is it like that? Now one answer is it could be just a historical artifact that somehow the very small creatures at the beginning of the evolutionary process developed this crossed over system because of the same principle as the eyeball and the retina, and then as creatures got more and more complicated, that was preserved. So that's one explanation, is it's just a historical thing. But there could actually be an evolutionary advantage to this. And the reason is, if you think about fighting, let's suppose you're fighting someone either with your fists or with a sword or something. Anyone do martial arts here, or fencing, anything like that? So you want to turn your body sideways so that you present the smallest possible target to your opponent. So if you think about it, I'm fighting my opponent, and if I'm turned like this, I'm predominantly using my right hand and my right eye for the fight, right? Now, if the right hand and the right eye were controlled by the right side of the brain, then if my opponent hits me with his club or whatever he's got, or punches me in the head, then that would reduce my ability to control my right hand, right? Because this side of the brain is being damaged. So it's actually, there's an evolutionary advantage to having the right hand and the right eye controlled by the left side of the brain, because if I get hit on the right side, okay, I get some temporary malfunction in my brain, but the left side of my brain is still intact, so I have a much better chance to keep fighting. Do you believe that? And in fact, some of these principles, we've talked a little bit about these reactive behaviors in nature with the wasp dragging the grasshopper into its nest and so on. If you have a look at small single and multicellular organisms, they observe this interesting behavior called chemotaxis, that they're actually able to swim towards a food source or swim away from a toxin. And some of these creatures are just single-celled organisms. So it's actually quite impressive that they're able to do this. And how does it work? Well, they've got a single cell like this, that's the cell membrane, and then on the outside of the cell they have all these little kind of hairy things that we call flagella, and they can spin either clockwise or anti-clockwise. If they spin anti-clockwise, then the flagella all kind of wrap up together like hair that's been braided or put in a ponytail, and that allows them to efficiently swim in a linear motion in one direction. Okay? And then if they spin in the other direction, it becomes this kind of tumbling motion, because the flagella are all sprayed out in different directions. And if you watch these little guys under a microscope, they're switching back and forth between these two modes of operation. So for a while they're spinning anti-clockwise and going in a linear motion, then they switch to spinning the other way and they're just kind of randomly tossing around, and then they switch back to linear motion and they're going to go linear again but in a different direction. So they sort of move linearly like this, spin around for a while, then move linear like this. So they're doing this kind of random motion, right? But then what happens is, if they detect that they're heading towards the food source, so they have little tiny sensors that can somehow detect that the concentration of food in the environment is increasing, right? And if they detect that, then the linear phase will be extended a little bit longer. So there'll be a slightly longer time that they're traveling in a linear direction before they switch to spinning again. Whereas if they detect that they're going in the wrong direction, so the concentration of the food is diminishing, then they'll shorten that linear period. Okay? And believe it or not, this is enough to get them to the food source. Right? If they're going in the right direction, they keep going a little bit longer. If they're going in the wrong direction, it's shorter. And over several steps, that actually gets them towards the food, and they can use this to move away from toxins as well. Right? So very, again, it's like very simple reactive behaviors that nevertheless will enable these things to survive in that environment. And people have built robots to mimic this behavior. I don't think anyone's built a robot, a single-celled organism with flagella and so on, but people have built robot models of the nematode worm that somehow mimics the reactive behavior of that little animal. And you can build Lego robots and so on, and do this at home if you're so inclined. Okay, now these ideas, Rodney Brooks kind of built on these ideas in the late 1980s and wrote a series of essays in which he challenged the traditional approach to AI as it was then, which he called good old-fashioned AI. And his essays are very interesting. So he draws this analogy. He says, let's imagine there's a team of engineers in the 1880s and they want to build an aeroplane. And a genie magically appears and offers to them, okay, I'll give you the opportunity, you can be magically transported 100 years into the future, into the 1980s, but you're only allowed to stay there for 1 hour. And during that 1 hour, they want to try to learn as much as they can about how to build an aeroplane. Okay, so the genie waves a magic wand, and they get transported into the 1980s, and they spend the entire hour on board a 747 jumbo jet in flight. Okay? And what happens? Well, the problem is they get distracted by all the wrong things. Okay, so they see flight attendants walking up and down the aisles, serving food, and they get distracted by that and they're talking to them, and then they realise, okay, that's something else, that's nothing to do with the flight. Then they see the in-flight movie. They've never seen a movie before. They're fascinated by that. How did they get that image up there on that screen? You know, asking all about that. And then they look at the materials that the plane is made out of. You know, these fold-down meal trays are made of some material they've never seen before. It's got a very interesting texture. It's very light and tough for what it is. Oh, that's called plastic. Oh, plastic. You know, so they think that it's all about plastic. It must be plastic that somehow makes the plane fly. Okay. All these other things. And eventually, after about 45 minutes, they get the idea, oh, we've got to go into the cockpit and talk to the pilot. So they go into the cockpit, but then they're just bamboozled by this array of sensors and dials and gadgets that appear in front of the pilot, and eventually the hour finishes, they get transported back home, and they've learned nothing useful. They have no idea about how to make a plane fly than what they did in the beginning, right? So the analogy is when we try to do artificial intelligence, we're in the same position as those people, that we have this direct experience of this very highly evolved kind of intelligence, and it means that we get distracted by the wrong things as well. So we're fascinated by these high-level tasks like playing chess and so on, solving puzzles, So what should those engineers have done? Well, they should have been studying early planes that had propellers and where you could understand more directly what was going on and principles of aerodynamics and so on. And so by analogy, instead of directly going to humans, we should actually start with insects. We should try to build artificial insects, then we can move on to a rat or something, and then if we can do a rat, then we can do a dog, and eventually build our way up to a human. This was the argument. And he argued in favour of a vertical decomposition instead of a horizontal one. So AI up to that point had typically followed what's called the sense, plan, act cycle. So you have information coming in from the sensors, and the idea was you'd have a series of modules. So first you'd have a perception module that does the visual processing and image recognition and object tracking, all that sort of stuff. Then the output from that would go to a modeling module. The modeling module would keep track of what objects are in the environment and how they're moving and so on. And then the output from that would go to a planning module, which would try to predict where these objects are going to be a little bit into the future and how they should be manipulated, what effect that's going to have, and so on. And then the planning module decides what to do, and then it goes into a task execution module, and finally to a motor control module to the actuators. There isn't necessarily always this large number of stages, but there's always this decomposition that things move along from one step to the other. And this was the theory, but Brooks sort of pointed out that by that stage there were very rare instances where anyone had actually connected something all the way through. You know, there were a few. There was a robot called Shaky in the early 1970s that actually was a complete system. It would actually, I should show you some, to try to dig up some videos where it moved extremely slowly, but it would try to solve these block world puzzles, and it would sit there for several minutes doing visual processing with whatever computing power was available. It was 1973, I think, and it would figure out where the, it had these blocks that were coloured with bright colours and so on, so it would figure out where the blocks were, and then it would plan, if it was given an instruction to put the blue block on top of the red block, it would actually plan and think, okay, I've got to move the green block out of the way first and then get to the blue block, and do this kind of planning, and then it would actually execute. So there were some rare cases where people had actually closed the loop and done the whole thing, but in general that didn't happen. In general, there was one group of people who worked on visual processing, and they had their own conferences, and then there was another group of people who worked on planning, and another group of people who worked on control, and these people, in effect, the perception people just assumed that the other people would be able to make use of the output that they produced, and the planning people just assumed that the perception and action modules would be provided in the right format, and so on, and these groups rarely spoke to each other, and so on. So what did he propose instead? Well, what's known as a vertical decomposition. So the idea is you have several layers of behaviors, from very simple ones up to more very advanced ones, but each behavior is able to connect sensors directly to action. So this fits in with those other pictures I was showing you, where you have, even in the most advanced kind of agent, you have perception and action and world model and planning, but it is possible to go directly from perception to action and bypass the rest of it. So the lowest level behaviors are just these kind of insect level behaviors that move along. And then at the next level you try to avoid bumping into things. And the next level up is a bit more sophisticated. You're exploring your environment, so this is where you need a world model. and map building, and then as you get further up, manipulating the world, then you need a planning module in order to plan several steps ahead. So we get this nice vertical decomposition of behaviors, and this is sometimes called behavior-based robotics. Sometimes it's called a subsumption architecture. Now, there was a fair bit of controversy over this. So Brooks's essays, I think there was one called Intelligence Without Reason, there was another one called Intelligence Without Representation, there were a couple of others. And people took umbrage at this and said, well, you know, this is all very well, but can you really have intelligence without representation? Okay, these bright and big vehicles are all very well, but to get up to higher cognitive tasks, you probably need some kind of representation, and there was all these debates, and eventually I think Brooks himself had to soften his own stance. And so the modern perspective on this is the following. So each layer in the vertical decomposition is a behavior. So instead of having a classification of agents, we have a classification of behaviors within an agent. So at the lowest level, you've got reactive behaviors, like avoid hitting things. And at the middle level, you've got building maps and so on, which makes use of a world model. And at the high level, you have things that make use of planning as well. So this nice kind of hierarchy. And this is also related to the brain in a sense, because there's this very primitive part of the brain that's the brain stem, which is sometimes called the reptilian brain. You know, there's structures at the very base of the brain are very similar among all mammals and even among reptiles. Like that part of the brain has changed little over evolutionary history. And then you've got these mid-level regions which are similar to what you find in our closest relatives like chimpanzees, but quite different from a reptile. And then you've got this, what's called the cortex, which is basically unique to humans. And so the cortex is where this high-level processing goes on. But if you get into a real emergency situation, like a bank robbery or a train crash or something like this, then somehow these very primitive structures in the brain take over and you find yourself behaving in a very reactive way, very according to your instincts. And in fact, when people are interviewed afterwards, these sensory channels, there isn't enough bandwidth to process all kinds of sensory information. So some people report that during the most intense part of the bank robbery, they could see but they couldn't hear. You know, they were not aware of the sounds that were going on in the environment, or sometimes it's the other way around. They could hear but they couldn't see, or whatever. So we've got these kind of instinctual behaviours that can take over in emergency situations. So that's the other debate that went on, is with this idea of the subsumption architecture. All of these behaviours are trying to affect the same actuators, so if they were all acting simultaneously, you could get a chaotic outcome. So somehow there's got to be this process that decides which behaviour is going to have control at any particular point in time. And so one behaviour can subsume another in the sense that it can take over and just block the other behaviour and force its own actions. And for a long time there was a debate, well, what's the more logical way for this to happen? Should it be the low-level behaviours that intervene and take over from the high level, or should it be the high level that take over from the low level? Which way around is it? And the consensus that's emerged is that it depends on the situation. It could go both ways in different situations. So, under what situation would a higher level behaviour want to take over from a low level behaviour? Well, let's say the low-level behavior is navigating, and the robot, there's a wet patch on the floor. On a rainy day like today, it's very likely for this to happen. So the robot could be just spinning its wheels and getting nowhere, but this low-level behavior may be unaware of that because it's just being reactive. It doesn't realize it's been in the same place for the last 5 minutes. So the high-level behavior may have to detect that the low-level behavior's got stuck and take over from it and switch to some new plan. It's like a manager who puts a low-level manager in charge of a particular project and monitors the progress, but then may decide after a while, okay, that guy's plan isn't working, let's switch and try the next guy's plan. Yeah. Okay, but then when would a low-level behavior take over from the high-level one? Well, again, it's these emergency situations. So robots, they might sometimes have a little sensor, little spring sensor underneath, so that if they get to the edge of a staircase, they detect that there's no floor under them anymore, and then they immediately back up to avoid falling down the stairs. These kind of behaviors have to be very fast in order to save you from a dangerous situation. And in humans, you see this as well. If you're cooking and you accidentally put your hand on a hot stove, it's a very fast reflex reaction that the signal doesn't even get up as far as your cortex. It goes up into your shoulder and possibly as far as the brain stem, and then you immediately pull your hand away. So it interrupts whatever else you were doing before, because you have to do it really, really fast. You don't have time to. It's easy to sort of make fun of this, but if you had to go through all of these steps, you can imagine, sort of. I accidentally put my hand on the stove. I detect a strange sensation of heat. What's going on? Something's burning. Is it my toast or is it the eggs? Oh no, it's my hand. Okay, my hand's burning now. Let me plan. What should I do about this? Okay, I could put water on it. I could turn the stove off. I could take my hand away. Yeah, taking my hand away would be a better idea. Okay, so let me just line that up as the next task to be executed. Okay, I'll take it off. Yeah, you don't have time to go through this whole sequence of data processing steps without getting burned. So it's a big advantage to have a way of short-circuiting that and just going directly from perception to action. And here are some references. So it's Breitenberg's book, Vehicles, Experience, and Synthetic Psychology. I mentioned Rodney Brooks' collection of essays. And there's this book by Rolf Pfeiffer and Christian Shire, Understanding Intelligence, which goes into a lot more detail about those sort of issues.